This is the fifth video in the lecture on the design of reinforced concrete beams, and we are now in the chapter of ultimate limit state. After this lecture, you will be able to calculate the needed tension reinforcement of a rectangular section under simple bending. In the previous lectures, we talked about the assumptions. In this lecture, we will talk about simple bending rectangular cross sections in domain 2A. If you look at the diagram of the strains, this is the unloaded plane. This is the loaded plane, and we know that the domain 2A for simple bending is marked with this left limit and this right limit. We have a cross-section, a rectangular cross-section with the tension reinforcement. We go to the strains, unloaded plane, loaded plane, and you will see in domain 2A, epsilon CUC, the strain in the concrete equals the maximum strain 3.5 per mil. The strain in the steel is between 0 and epsilon UG, but we are choosing here 10 per mil. This is between 0 and 10 per mil. Then we go to the stresses. From strain to stress is by integration, and the same happens with the stress in the reinforcement, which is just the modulus of elasticity times the strain. At level of the section, we have the total compressive force, Fc, equals Cx FCdB. It is nothing more and nothing less than this rectangular FCD times X times the B, the width of the section. So it's an integration, but now we have calculated too much because this portion is not there. So that's why there is the filling coefficient psi. We know that psi is 0.81 in domain 2A, and it stays constant in domain 2A. We have the total tension force in the reinforcement, and the distance between those two is equals to the lever arm Z, which is d min delta G Gx. Delta Gx is just the position of the total compressive force compared to the most compressed fiber of the section. And this must be in equilibrium with the applied force, which is just a bending moment. Now, before we go any further, we will put forward some dimensionless coefficients or symbols where we will work with. The filling coefficient we know by now. The coefficient of the center of gravity, delta G, we already handled this. The depth of the neutral axis, it is x, but we will divide it by the effective depth so that we have a dimensionless unit, which is called xi. The lever arm zeta is just the z divided by d. The reduced bending moment is the applied bending moment divided by bd squared FCD. And the mechanical reinforcement ratio is ASFAD divided by BD FCD. General principle. We start with the stress-strain relationship of concrete, and we calculate the filling coefficient, the psi, and the center of gravity, delta G, by integration. In the next step, we use the compatibility. It means we use the rule of similar triangles. The section before loading stays straight. If this section before loading is straight, it stays straight after loading. Then we use the stress-strain relationship for reinforcement. we use the equilibrium translation, the translation equilibrium, by stating that the compressive force in the concrete must be equal to the tension force in the reinforcement. And we use also the rotation equilibrium. That means that the acting bending moment must be equal to the resisting bending moment. Now, if you use these principles, and we start with the first one, in a strain diagram, if we zoom in on the strain diagram, you will see that if you take at the neutral axis S equals 0, and on the top S equals x, x is the depth of the neutral axis. We know in domain 2b, 2a, the most compressed fiber, there the strain in the concrete is 3.5 per mil, and there is 0, so we can easily write the relationship of the strain in the concrete as a function of a coordinate S. If we now look at stresses, it's first parabolic until you arrive at 2 per mil, and then it goes in the rectangular section. We know by definition that this distance is delta gx. This is our coordinate. We start with the neutral axis equals 0, and it goes up like that. And it goes up until S0, which is the border between the rectangular and the parabola, and it goes until x. Now, this is a simple figure to help you integrating, to help you making the right equation. For a translation equilibrium, then it's simple. It is the rectangular. It's x times FCD times the width of the section. So that's the whole rectangular section, but we have not the whole section, we have a portion of it, so we use the filling coefficient psi. That's in fact by definition. We are looking for the psi coefficient. So we make it equal to the integral, of course, of the stresses in the compression zone between 0 and x over the coordinate ds. We know the relationship of sigma c for the stresses, for the strain relationship. If we fill this in and we calculate the integral, we will find that psi is equal to 0.81. And it is independent of another coefficient. So in domain 2a, psi is always 0.81. Now we look at the rotation equilibrium at the neutral axis. Then it is the lever arm, 1 in delta G, times x, times Fc, the compressive force of the concrete. And this must be equal to the integral, the coordinate S times the stress times ds, and we integrate from 0 to x. If we calculate this and we fill in Fc, like we found here, because this portion is Fc, we fill in psi also, then we find delta G, and we see that delta G is also independent of another coefficient. It's only 0.416. So in zone 2a, psi and delta G are fixed. They do not depend on the depth of the neutral axis or something else. Then next, the compatibility rule of similar triangles. Remember, this is the picture that we started with in domain 2a. If we look at the strain, then you can see that epsilon CO2 is known, that's 3.5 per mil. Epsilon S not, it's between 0 and 10. So now we can just express epsilon S in function of the known strain in the concrete. So we just use the rule of similar triangles. It's just epsilon S divided by this side must be equal to epsilon CO2 divided by x. We get epsilon S from that, and we use the dimensional units of xi, which is x over d. And then you see that epsilon s equals 1 minus xi divided by xi times 3.5 promille, or epsilon Cu2. So we have a direct relationship between the depth of the neutral axis and the strain in the reinforcement. Depending on the domain, there is always a relation between the known and the unknown strains. So in domain 2A, this is this relationship. Why? Because in each domain, there is some point, some pivot point where you know what the strain is. So the known strains is the pivot points of the strain diagram. Next is the stress-strain relationship of reinforcement. It is straightforward. It's a bilinear diagram. If the strain is less than FAD divided by ES, ES is the modulus of elasticity, then it's simple. The stress equals modulus of elasticity multiplied by the strain. And if epsilon s is bigger than FAD divided by ES, then sigma s is yielding, the steel is yielding, and sigma s, the stress, is equal to the FAD. For BE 500, epsilon s at that particular point is 2.17 promille. So this means if your strain is bigger than 2.17, the steel is yielding, and you can use 435, which is 500 divided by 1.15, as steel stress. If it's less, then you use the linear relationship. Simple as that. Next is the equilibrium. An equilibrium in the translation direction. The compressive force in the concrete must equal the tension force in the reinforcement. If we take now the compression force, Fc must be equal to Fs, and Fc we know now is the filling coefficient times xb FCD equals the force in the reinforcement, which is the total area of reinforcement multiplied by the stress. We can regroup this equation and take As out of it. We use the dimensionless unit omega and xi, and if you substitute it, then you have the relationship omega is psi xi FAD divided by sigma s. We take a rotation equilibrium where the acting bending moment equals the resisting bending moment, and the acting bending moment is md, and we will take the bending moment around the tension reinforcement. So it should be equal to the force in the concrete Fc multiplied by the lever arm Z, which is d min delta Gx. So Z is d min delta Gx. The force in the concrete is fillings coefficient times xb FCD, and that's equal to the bending moment. Now we work it out to use the dimensionless units. So we divide by BD squared FCD, and then we arrive at this equation, which is nothing more than a rotation equilibrium around the tension reinforcement. Nothing more, nothing less. This equation here is identical to this equation. But this equation depends on the sizes of the section. This is a universal equation because it's with dimensionless variables, so it's applicable to all sections, rectangular sections. Then we can also have a rotation equilibrium, but then around the compressive force. That's the same. So the acting bending moment is then equal to the force in the reinforcement times the lever arm. If we make it now dimensionless and we use zeta equals z over d, then we arrive at the formula to calculate the reinforcement with the lever arm zeta. This is only valid if the steel is yielding. Otherwise, we have to do something else. The lever arm of concrete compressive force and tension force of reinforcement. If we look at this lever arm, Z, then Z is d min delta Gx. Z over d is then, I just divide by d to make it without dimensions. Then we got zeta and xi. And this is the relationship between the lever arm and the delta G times the position of the neutral axis. Now, all those dimensionless formulas, because they are independent of your section, they are worked out in a table, which is this one. This is a table for concrete class smaller than C5060 with epsilon ud equals to 10 per mil. And then you will see that in the first column you will have mu d, in the second column omega, and you have all the dimensionless variables are linked in this table. We will see that epsilon c, the strain in the concrete, is 3.5 per mil, which is domain 2a. The strain in the steel varies between 0 and 10 per mil, which is what we want. The psi, the filling coefficient, is 0.81 because we know this is constant in domain 2a. Delta G is constant, 0.416. And these are the stresses in the steel, but we are most likely working with BE 500. You will see it's varying at the end when the steel is not yielding. So this is a very important point here, 0.371, because that's a point when the steel is not yielding. The equations, mu d can easily be calculated. Omega is psi times xi. And zeta is the same formulas that we derived in the previous slides. And epsilon s. So you can use directly all those formulas, or you make it for yourself easy and you use the table. We will see how we can do it in a practical way. Now, when are the following three equations correct? And what is in fact the physical interpretation of it? Because they are all dimensionless. They are always independent of a unit, of a dimension. The first one is always valid because it's nothing else than the bending moment equals the concrete compression times the lever arm. The fillings coefficient times the depth of the neutral axis. So this is the physical interpretation. It's just the bending moment equals concrete compression force times lever arm. Always valid. The next equation is only valid if the reinforcement is yielding, because in this equation missing here is the steel stress divided by FID. And if sigma s equals FID, then it's 1, then you get this. So this is only valid when the reinforcement is yielding. The physical interpretation, the tension of the reinforcement equals the filling coefficient times the depth of the neutral axis. It is just a translation equilibrium. It's just the force in the reinforcement equals the compressive force in the concrete. And the last equation is only valid when the reinforcement is yielding, and this means that the bending moment equals the tension in the reinforcement times the lever arm. Now let's summarize domain 2A. We have a rotation equilibrium with respect to the tension force in the reinforcement, gives us this equation. We have the translation equilibrium, and it gives us this equation. The reinforcement is given by this formula. And we know in domain 2a, delta G and psi are constant. If you look at the strain diagrams, we know that this is domain 2a with sigma s, with the strain in the steel is between 0 and 0 promille. On top, it's always the strain in the concrete 3.5 promille. So we are in this triangle. The left border is with the neutral axis at a depth of 0.259. The reduced bending moment is 0.187. The right border, it's simple, x equals d, so xi is 1, and mu d is 0.473. So what does it mean physically? It means that if you have a bending moment and you calculate the reduced bending moment and you find a figure which is bigger than 0.187 and smaller than 0.473, you know you are in domain 2a for calculating your reinforcement. If it's smaller, then you are outside it. If it's bigger than 0.473, you have a problem because this is the maximum value for simple bending. If it's 0.5, your dimensions of the section is not big enough. You have a problem. There's an absolute maximum. Then we got a third line, the dotted line. This is the point where the steel is yielding. To the right, the steel is not yielding. To the left, the steel is yielding. This is also a very important limit. We'll see why. And this limit is 0.371. And the corresponding xi is 0.617. So this is the summary of domain. Now let's look at the left border of domain 2a. We know in the left border that epsilon c is 3.5 and epsilon s 10. Then we can go to the stresses in the concrete and the force in the concrete and the force in the tension reinforcement. Now, what we want to do is to calculate mu d for the left border and the xi for the left border. We know for domain 2a, psi and delta g are known. Xi is just x over d, and it's equal by similar triangles to 0.259. So in the left border, the depth of the neutral axis is always 0.259 times the effective depth. The mu d equals this. We have all the variables for the left border. We can fill it in and we find 0.187. So now we know that if you use steel and concrete to their maximum strain for simple bending, your mu d is always 0.187. And the zeta for calculating the reinforcement is just filling in the different values, and you have 0.892. So it means for the reinforcement, it's md divided by zeta d fad, so you have a simple relationship between the reinforcement and the bending moment. This is for the left border. Now we look at the right border of the domain. That is the right border. We see that epsilon s is 0, epsilon c 3.5. This stays the same. We calculate xi, and xi is x over d. It's simple, x equals d, so it's 1. And mu d is just you fill in the different values of this equation, and you have at 0.473. And zeta is then 0.584. You see that the zeta here is very small. So on the right hand side of domain 2a, you are not very efficient with the reinforcement because it varies from 0.9 up to 0.58. So the smaller this number is, the more reinforcement you need for the same bending moment. So avoid the right hand side of domain 2A because you are wasting reinforcement. Now we will look at the yielding of steel in domain 2A. You have the strain diagram for the concrete is 3.5 per mil. For the steel, it's equal just at the point where the steel is yielding. It means this is for BE500 equals to 500 divided by the material factor, which is 1.15, divided by the modulus of elasticity of steel, which is 200,000. So you have 2.17 per mil. Then we know that C and delta G is constant, epsilon C is fixed, and epsilon S is 2.174, so which is here. And then we can calculate the depth of the neutral axis, which is always the same. It's this one divided by the sum of the two, and it's 0.617. So at the position of the lever arm equals to 0.617 times the effective depth. At that point, the steel in the tension reinforcement is just yielding. Then we calculate mu d and we find 0.371. The lever arm is then equals to 0.74. So if you calculate reinforcement, you have to divide here by 0.74. It is of great importance that you should always work on the left-hand side of this diagram. Why? Because you want the steel to be yielding. You do not want to work with steel which is not yielding. It's a waste of money. We can now calculate the needed tension reinforcement of a rectangular section under simple bending. See you next lecture for some practical examples.